10 people helping. So we get 8. You can see everything, all right? It's just very small, but zoom in. The lab assistants and office hours. I'm requesting office hours for each TA. So 2 of them already responded. So they have Tuesday. Walt has Tuesday from 11 to 12. And Kenny has Wednesday from 3 to 4 p.m. And other people's office hours will be posted to this website. It's just on the top of the course website. You know where to get here, right? It's electronics.com, and click E383, so you can get to this website. You can see all the schedules and everything. Okay, so for example, section A, and I will be in section A as well because that was assigned to me. So I'll be there in the early morning from 8 to 10:50, I think, in the morning to help you guys. And after that, I probably will stay there or leave. I don't want to stay there for the whole day. It'll be like 10 hours or so. I would love to. I love students. It's just too much. But I think for most of the time, I will be in my office or somewhere else. But if TAs have any questions, they will probably just directly call me or email me. I'm having meetings with the TAs one day before. So on Wednesday night, we have a Zoom meeting. So I'm going to go through everything. They already taught that before. That's what I heard. So they're experienced. And I'm going to have a meeting with them on Wednesday to keep everybody on the same page. So they know the tasks. They know how to do the demo, run the demos. Because every lab has a different task. For example, lab 1. Depending on the materials of the lab, so we have to do different things. Okay, so for example, lab 1, we don't even have any C code in there. You are not coding anything. It's a hex file being compiled from the C language as a C code from Dr. Colston, and we haven't learned anything yet. So it's going to be just a hex file. You can directly download it to the microcontroller. So it's trying to let you know what the microcontroller does, I think. What are the functionality of it? Or modules, blocks. There's blocks on the board. So if you follow all the steps, definitely you can always go back to Dr. Colston's website. It's basically the same stuff. I even copied his text into my website. But the difference is I have all the pictures because I went through that myself. So I took snapshots and recorded videos as needed and posted to the website. So showing step-by-step procedure. I think it will be easier compared to his website. I follow his website and I got everything done. So if you follow his, you can also get everything done. I'm pretty sure it just takes more time, I think. So this one just shows you the pictures. When you see this interface, you want to click where and select which option. And also I have all the numbers for each task. For example, task number 2, you see here, it's a task number 2. So it's task 2, right? Task 2 is for task number 2. Task number 2 is the task number on his website. So if you look at his website, you can see task number 2. So that's for you to refer to his website, you know what's going on. But it's task 2 for this lab on my website. Sorry, it's a little bit confusing. It's just for lab 1. For the following ones, it's easier. It's not always having 10 tasks. This one is having 10 tasks because all the tasks are super simple. You get a hex file downloaded to the microcontroller. You just keep pressing the push buttons. You can get everything done. It's super simple. That's why there are so many tasks. So whenever it's getting into the later ones, you'll see the numbers are not matching. It's a test number 10. Remember the number 10 or the test numbers are from his website. Okay. The reason for that is because I removed probably test number 9 because it's too simple or it's for a lot of different reasons. I just removed it, so you don't have to do it. You know what I mean? So this will be all the tasks you have to do, but not all the ones on his website. Sometimes I'm adding things, sometimes I'm removing things, but this will be the deliverables are all listed on my website. Is that clear? Okay. So you have to do a report, and I also changed my mind. You don't have to do individual reports. For a group, 2 people, no more than 2 people, you can have just yourself working on your one group. It's okay. If you just want to work by yourself, you want to learn more things, it's okay. Okay. But if you want to form a group with 2 people, it's also allowed. You can have no more than 2 on each team. However, just one report each team. So I'm expecting if we have almost 100 students in the class, right? So you have 2 people on the team, each team, there will be like 50 reports for the grader to grade. Not too bad. You know, I'm pretty sure there will be students want to just be on one team by themselves. So that will be probably eventually like 65 to 70 group or reports to grade, still within a reasonable range. So what to be included into a report? Since I'm having a meeting with the TAs tonight, okay? So I'll let them know. But however, this is recorded. If you see any differences or conflict, just refer back to this video, okay? Since I'm gonna say the same thing to the TAs tonight, as recorded. And the template will be this one. You can click, it's on the top of the page, there's a lab report template. Because you are only demonstrating one task out of 10 to the TA, okay? So I want a TA know that you have done all of the tasks, so the rest of the 9 tasks are not going to be demoed to the TA. So I have to put in the report. So here's the report. Some of the tasks have requirements for videos, and some of them don't. It's just snapshots and very briefly explanations. It's not a composition, or it's not a writing class, not an English class. Engineering, let's keep it simple. And I was looking at the ABAT requirement. It's not requiring ABAT outcome number 3, which is communication, writing, communication, presentations, things like that, right? So it's not requiring. However, for the final project, we still need a presentation from each team. So still getting that outcome for ABAT, but they're just not going to use it for evaluation or assessments. So things like this, right? So you have the title, in lab and lab 1. Team members, make sure you have the team member's name on the top so the TA can log the grades for each of you on the team. And task 1, if it's just super simple task, you connect to the board, you run the code, push a push button sometimes, it's gonna show all the text in the serial monitor. It just take one snapshot, very simple, one snapshot, like what I did in the report, in the tutorial. And so do you know how to make a snapshot, right? Snipping tools in Windows. For MacBooks, it could be a different tool, but similar stuff. Just snapshots, copy and paste to a Word file. If you use LaTeX, it's okay, but eventually it's gonna be a PDF file to be submitted, one single PDF.
For the lab, will we be able to use a Mac, or will we have to use
You mean for the EDA tool,
Yeah.
for the programming? So I didn't try Mac, but if you go to, I'll click later. Okay. Here, you'll see problems with Mac. Okay. Installation hints for Mac users. Try it. I've never done that before, but let me know.
So for the lab, basically, are we using Colston's site or the lab document on there as like the steps, and then only doing the tasks that you specify on your site?
No, all the tasks are on my website. So his website is the original document that I used to generate my lab tutorial. So all the tasks are specified in my lab. So let's take a look at it. I'm going to show you on my
So just
website.
follow yours.
Follow mine, yeah.
Okay.
But sometimes I assume that I just don't want to directly duplicate everything because it's just already there. So I will just let you refer to his.
So just read the descriptions on his and then follow your steps.
I think follow mine first, and then if you need to refer to his, just refer to his. Because all the tasks are listed at the bottom of the page. So for example, for lab 1, so for the following lab, for all the rest of the labs, it could be different, slightly different. That's a very good question. It could be slightly different. But let's just say lab 1. Pretty much you don't even need to look at his lab 1 tutorial at all. Since all these steps are super simple, and I make every single snapshots for every single step, you just follow. I think most of you will get the same results. If you see like bugs or some troubles, you can always refer back to his website or ask the TA during the lab. So let's scroll down to the bottom. It's a pretty long tutorial, but very simple. So see all the tasks. So basically you follow all the steps at the very beginning of the, for all the rest of the page, and then come down to the bottom. You will be able to know what you have to finish for this lab report and what has to be demoed to the TA. So for example, how many demo tasks we have for all the tasks? Just one, right? In-person demo will give you 20 extra points. Okay, so hopefully this will keep you engaged, keep you come to the lab. Sometimes we will give quizzes. I don't know yet, because every time we give a quiz, it's going to be 100 quizzes to grade. So I have to be very careful about that to keep it in a reasonable task workload for the TA. However, we do need the quizzes. That's one of the best ways to keep students engaged and come to the lab. However, if we don't have demo tasks, probably you just finish everything at the dorm or in the apartments, and just post everything to YouTube. Okay, then the TA will grade it. You get full points. It's not the perfect situation, I think. I hope you guys can come to the lab and work with the TAs. And there will be some of the cases that require you to use benchtop equipment. I got a typo here. Oscilloscopes, for example. So this one is an in-person demonstration. So because we have to use the oscilloscope to probe the circuits. And not all of you have oscilloscope at home, right? None of you have it, probably. Is that clear? Any questions? So we have regular tasks, we have demo tasks. For this lab, at least. In the future, I think I was looking at lab 2, since I created a few weeks, 2 months ago, I forgot. I was looking at lab 2. I was like, only 3 tasks. 1, 2, 3. Probably all of them will be demo tasks. Probably I have to ask you guys to do both. Because 3 tasks are not really difficult to demo to the TA. I think if you have 2 people on one team, we have 25, theoretically, 25 students for one section, right? If you form 2 people each team, that will be about 12, 13 groups. So 13 groups times 3 tasks will be 39 demos. Not too bad for 3 hours. And you probably won't be able to finish everything during the lab time. So I have to find the TA's office hours to run the demonstration during the week. And for the following labs, it's getting more and more difficult. The in-labs are easy. What I heard is in the past, almost 100% of students are able to finish in-lab during the lab time. So that's what that was designed for. So actually, in-lab is doing in the lab. And they should finish everything in the lab. And then follow in the following week, they will have to work on the project for that lab as a homework assignments and demonstrate it to the TA. You have to find out specific time and appointment with the TA to get it demonstrated. I think it's making things very complicated. But we just have to do it. So that's why I combined both. So you will work on the in-lab. If you finish it, moving forward with the lab. If you are getting lucky, you finish everything during the lab time, just demonstrate everything to the TA. Okay? That's for lab 2. For homework assignments, if you look at the schedule, I also posted to Canvas. Homework 1 is due Thursday next week. One single PDF submitted to Canvas. This is straightforward, right? Okay. So I think organize everything this way will be really beneficial, since we have all the lectures and labs organized on one page, and you see the week 1 schedule is just everything for week 1, nothing else. It just look at week 1 schedule. There are 4 things to do, right? So 3 lectures, 1 lab, 1 homework. Definitely lab. You click into that, you can see Some of them are required to be put in the lab report. Some of them are demo tasks. That's it. Is that clear? Week 1, that's everything for week 1. Week 2, that's everything for week 2. Okay? Questions? Okay. Let's take a look at the board because tomorrow you have to not program, just download the hex file to it. Let's take a look at it. So that's a schematic of the code of the board. Being joined Eagle PCB. Before I do anything, let me ask you a very simple question, circuit 1 question. What is GPIO? Yeah, it's the I/O ports for the digital circuit, right? Focus. So what's the name of the 10K resistor? What's the name of it? Yeah. Pull up. Why? Is it pulling up anything? You couldn't see it, right? Just a resistor connect to the 2 terminals. Why is pulling up? Let me ask you another question. You got a power supply, you got a resistor here. Okay, 1 megohms. What's the voltage here? I think we talked about that last time. What's the voltage here? Why not 0? What is 0 volts? What is 0 volts?
The ground. It would be 5 volts because it's not connected to another load. Or it's not completing the circuit.
It's not completing the circuit. So if it's not completing the circuit, why is it getting 5 volts? No current. That's right. That's the correct answer. What's the current?
0.
Again, no worries. No worries. Everybody, feel free to ask any questions you have. Okay? Current is 0 amps. Good. So you guys are electrical engineers, right? I have high expectations. Whatever you are talking, it should be professional. 0 amps. Okay? So according to Ohm's law, what is Ohm's law? Find a different way to say it, especially during the interview.
The voltage across the component is proportional to the current times the resistance.
That's good, but is there another way to say it? That's good, but is there another way to describe it? That's right as well. Both are correct. Okay? So if you run the current through a resistor, what's going to happen?
It's going to cause a voltage drop.
Yeah, there will be a voltage drop. That's Ohm's law, actually. That's it. I mean, you can describe it in all different ways, but as an electrical engineer, let's just always seal this in your mind. Okay, you got a current flow into a resistor, through a resistor. You got a voltage drop. Okay. So you got a VR. Okay. So if the current is 0, what's gonna be what's the voltage drop?
0.
V equals IR, right? So we're getting 0 volts. Drop. No drop. So what's the voltage here? Compared to where?
0 volts.
Yeah, compared to ground. So I'm getting 5 volts here. So why I'm saying, yeah, voltages are relative, all relative, right? They are just differences between 2 nodes. But why it's valid to say a voltage at a certain point? Why I can directly say the voltage here, the voltage there, the voltage is what? Why I can say that? Why it's valid?
Are you saying why can you or why can't you?
Why it's valid? Because all the voltages are relative. They are just differences, right? It should be 2 points. Subtraction of 2.1 subtract another one.
You define the reference point using the ground symbol.
Yeah. You're trying to say the same thing?
Same thing.
Cool, okay. So that's why I can say the voltage at this point is 5 volts, because I'm comparing this point to 0. So that will be VA minus VGND, which is VA minus VGND, which is 5 volts minus 0, which is 5 volts, right? So that's why I can say it's the voltage at this point, because it's minusing 0, minusing nothing. It's still itself. All right. So voltage here is 5 volts. No drop. So voltage here is 5 volts. Compared to where? Compared to ground is 5 volts. So now I can see it's not 0 volts. Even though we don't have anything connect to it, but it's not 0 volts. What is 0 volts? Ground. Circuit 101. Cool. All right, let's come back to this problem. What's the voltage of VDD usually in the digital system? Let's say 5 volts. I think, actually I forgot. I mean the peak system probably is 3.3 volts instead of 5. Anyway, let's say 5 volts. Okay? Same situation, same circuit. Right? So this little bar here is the power supply. I just draw it like a battery. It's going to be the same thing as this thing. Okay, supplying 5 volts to it. What's the voltage here? 5, because there's no current, no voltage drop, right? So that's why it's pulling this up to 5 volts, even though there's no a little person here in the circuit pulling it up. No, it's just pulling it up by the voltage. So pull-up resistors should be in which range? Should be like 1 ohm, 10 ohm, or 10K, 20K, or 1K. Is 1K or okay a good pull-up resistor in general? No. Pull-up should be usually like 10K and up. Okay, 10K to 20K probably. 1K is too small. Why we don't want to use 1K, anything below 1K? Oh. It's bad, right? Why? Why anything lower than 1K is bad?
Because we want to resist so that, because the chip needs to hold down that GPIO, and we don't want to need the chip to take in a bunch of current, so we need it to be weakly pulled out.
Yeah. Let's just.
I mean, yeah, same thing. Just we don't want a high current running through the circuit.
Yeah. Because low resistance will give you a high current. It's just being used as a pull-up. It's not a function. It's not a functional component, or it is, but it's not that way functional for the circuits, right? It's just pulling up. So 10K, 11K, 12K, 15K, 20K, all of them works. In different situations, you have to choose different resistance. For example, I2C, you'll deal with I2C in the future. It's a serial, just one-liner, serial communication protocol. And depending on different transmission frequency, you have to pick up different resistance in a lot of cases. Don't need to worry about that for now, but just let you know, in most of the cases, especially for the first few weeks, we usually just use 10K. So that's why when you look at the schematic, you still couldn't see it clearly. It's not helping too much. Could you see this schematic here? So see a 10K, and you see this little power supply, and you got 2 switches. And these are push buttons on the board, push buttons. So if you push it, it makes the connection to where? To ground. Okay, so if you don't push it, what's the voltage at this point? VCC, okay, which is the power supply, because of the yeah, cool. Got it? If you push it, what's going to happen? To ground. What is that? From VCC drop to where? Yeah. So VCC minus 0 is what? Yeah. So what's the voltage at this point? Why? It dropped from VCC to 0. Another way to look at it is, if you push the push button, what's happening to this point?
It's being grounded.
It's being grounded. Or another way to say it is, it's shorted to ground. Okay? That's how I'll say it. You push the push button, you short this point to ground. That's it. Okay. So now let me know why you don't want to use. I know you already answered that question. But if you push it, what's going to happen? If you push it, yeah, it closes the circuit. It closes the circuit. It closes the circuit, so the only component in the circuit is the resistor. And it's going to be 5 volts divided by the resistor will be the current. So if the pull-up resistor is like 1 ohm, what's the current running in the circuit? 5 amps. Is that a big current or small current? Yeah, huge. Probably it's not true, but what I heard is if you run 200 milliamps, 200 milliamps through a cow, it's going to kill the cow. 200 milliamps through the body of the cow. Okay? So if you, but why, for example, if I use my finger to touch a 2000 volts, it's okay. For a voltage multiplier I built from a USB. What's the voltage for USB? 5 volts. Last time on Monday I talked about that, okay? I'm going to repeat that in the future. So 5 volts for USB. I can use USB plug-in here and step it up to 2000 volts, right? If I touch the 2000 volts, I'm still fine because the power supply is tiny. The power supply doesn't have enough power to supply the current to kill me, okay? The reason is my finger has high resistance, okay? So if I remove the skin and expose my blood vessels and have a less resistance, I'll probably still be fine because the power is still low, but it's higher risk. You got it? I'm touching 2000 volts, but never getting 200 milliamps to flowing through my body at all. You know 200 milliamps is gonna kill a cow. Probably it's gonna only take like 50 milliamps to kill me. I don't know. I mean, 100 milliamps. I don't know. But just let you guys know, amps is a very high unit. Okay. Another high unit is farads. The capacitance is also a high unit. 1 farad is huge. Usually in digital electronics, like you guys are microelectronics people, and microfarads are really huge. We are dealing with usually picofarads. And if you are doing integrated circuit design, it's usually femtofarads. So femto is 10 to the negative 15th, right? 10 to the negative 15th is the level. Usually it's like 20, 50 femtofarads in the integrated circuits. Okay, picofarads is really huge. I was able to build like 20 picofarads capacitors on the chip. It's already taking like 30% of the area of the chip or the die. The little tiny integrated. For example, I can let you take a look at it actually. So there was one project we did in analog electronics at the Fort in 2018 when it was still free. We sent the design. It was op-amp. We designed the op-amp. Here, that's the op-amp. And we also designed some of the gates. You couldn't even see it. It's tiny. So it's a inverter or something. I think I still couldn't see it because the wires are way bigger than the chip, in the transistors. So it's just a little tiny thing over here. And that's the op-amp. And this is a 40-year-old technology. 500 nanometer technology. So the smallest the transistor can build on the chip is actually 2 times 500 nano. It's almost a 1 micron. So the transistor size is 1 micron. But you can still use somewhere around like 40 transistors to build an op-amp. You're going to use op-amps. You will write circuit 1. You know op-amps, right? Mm-hmm. Amplifiers. So this is usually what the amplifiers look like, because usually we make it into the rectangular shape. You have the 2 rails on the top and bottom, so you can align to other modules, top and bottom, power and ground. So that's why they are usually organized that way, and you connect them to the pins. That's 70 micron, okay? Just let you guys know the scale. And the whole chip is just 1.5 milli. It's under the microscope. So the whole chip is only 1.5 millimeters, which is from here to here, okay? So that's the breadboard. You have seen breadboards, right? So it's a good reference, that's a scale. And here's a chip. So that's a chip, okay? And these are the bonding wires you couldn't even see. There are super thin gold wires. I have 2 rows of the gold. I shouldn't let you guys know. It's most expensive stuff in my lab. 2 rows of pure gold wires that they can bond to the chip. Use a wire bonder. $50,000 equipment, is gonna do the job. And you connect to the board, test the amplifier. And this is inverting configuration, so you can see it's getting a 180-degree phase shift. And this is just voltage follower. It's following, duplicating. So it works. Okay, so that's size of the op-amp with the 40-year-old technology, but still tiny. If you compare to the modern ones, for example, 68 nano still being used as for analog design. For analog design, 68 nano probably is 10 times smaller. So imagine using modern technologies, you can make op-amp 10 times smaller than this. Okay, that's the size of the op-amp on the chip. All right. Any questions regarding the schematic? There are a bunch of other things. The microcontroller itself, and this is a USB to serial converter in front of it. So tomorrow you have to use the low-pass filter with the op-amp, and speakers over here, a couple other things. It's a pretty good design, okay? So let's talk about the homework really quick. 15 more minutes. We have Friday to talk about that as well, so no worries. It's due next Thursday, so we have time. First, check logic, fundamentals of logic. A10 A10, let's say and. So no questions are stupid questions. Feel free to ask questions anytime. Maybe you are helping other people as well because they may have the same question. Okay, I'm serving 100 students, not just 5 or 6. Even though they are answering questions really quickly, they have more experience. That's all right. Just ask questions because 90 of you guys don't know the answer and don't know the details. You come to the class to learn. Feel free to ask questions. Okay. This is something you learned. I've learned in logic. A and A. A and 1. A and 0. 1A. Same. Right? 1 1. 1 0. 0A. 0 and 1. 0 0. Cool. A or A. A or 1. A or 0. A or 1. Same, right? 1. 1 or 1. 1. 1 or 0. A or 0. 0 or 1. 0 0. 0. So I'm skipping not just, inverter, right? XOR. Just think about it. A XOR is what? Yeah. They're the same, right?
Yeah.
Okay. This is something you need to know and still in your mind for the whole semester. It's going to be used all over the places. All over the places. That's right. So keep in mind. Keep in mind. If you XOR something with 1, it's going to toggle it. Okay? Don't use other words. It's just electrical engineering specifically, term to be used. So if A actual 1, A will be toggled, right? Will be A naught. If A XOR with 0, will still be A. How to verify it? Truth table, yes. So you just assume A to be 1, right? So 1 XOR 1 will be 1. So it's the same, but 0, yeah. Oh, sorry. So 1 XOR 1. So if A is 1, right? This will be 0, so it's inverted. And if A is 0, XOR 1 will be 1, so it's inverted always. You don't have other cases, it's binary. Unless you are doing quantum computers, it's different. But it's going to be 1, 0, just two states. So logic 1 in a 5 volts logic, logic is what kind of voltage? So if for example, I grab the board, you are looking at the microcontroller. Arduinos are 5 volts, okay? So the PIC we are using probably is 0.0 volts. I forgot. I can't look at it. So the logic 1 for the whole digital system will be the power supply. Okay? For Arduinos, logic 1 will be 5 volts. For PIC, if it's 3.0 volts power supply, so logic 1 will be 3.0 volts. They are both logic 1. Why is that? Because in integrated circuits, all the digital logics are formed by all the gates. And these are just 2 rails. It's a power rail, and that's a ground rail. So whenever you have the output, for example, this is the input, this is the PMOS, this is the NMOS. It's okay if I haven't learned that yet. Just let you know, there are 2 transistors, complementary MOSFETs. That's why it's called CMOS. Complementary metal oxide semiconductors. So the PMOS, P-type and N-type. And if you give an input like 0 volts over here, and 0 volts will turn on the PMOS and turn off the NMOS. If you turn on this guy, what's going to happen for the output? Here's V out. If you give a 0 volts for the input to the logic gate, to the digital gate, I told you it's turning on this transistor, so it's getting current flow. So this point is being what?
5 volts.
Yeah. Another way to say it?
Logic 1.
Yeah. Another way to say it? Because this is turned on, right? This is turned on. What's going to happen? It's pulling this up, right? Pulling this up to the power. So that's why you're getting 1. It's different from the pull-up resistor. It's different because this is totally off. It's just disconnect circuit. Or you can say it's shorted to power. Either way. So you're getting 1. Okay? If you give a logic 1 or 5 volts, 5 volts will turn on this transistor, the bottom transistor, so this one will be off. Okay? So what's going to happen? This one is shorted to ground. So you're getting 0. So that's the inverter, how the inverter works in integrated circuits. So if you use PMOS and NMOS, sure. If you use different transistors, different circuits, learn VLSI, you will be able to learn how to form different logic gates using PMOS and NMOS. You can form all different kinds of gates by doing that. That's why when you feed a certain voltage to the input, you are getting a certain output, and that output will be either shorted to power or ground. And because you have a power shorted to 5 volts or 0.3 volts, doesn't matter which one you are using, and you are getting output or logic waveforms, because the digital circuits is always outputting a digital signal. So it's either 0 or VDD. VDD is the power, 5 volts or 3.3 volts, depending on your power supply, right? Does that make sense? Questions? I think these are easy. Let's just go through that really quick. Binary to decimal. Let's just give shorter example, easier examples. 101. This is 2 based, right? It's 5, yes. So this is 2 to the second, right? and this is 2 to the first, and this is 2 to the zeros, right? So you add them together, but you have to multiply the number here. That's 0, and that's 1. So you're eventually getting 4 plus 0 plus 1, right? It's 5. And if you convert decimal to binary, notice this is recorded. You can always revisit the lectures after the class if you need. So decimal to binary, you are dividing this number by 2. For example, 25, okay? Divide by 2. The first time you are getting 12, 12 point, but digital, right? So don't have 0.5. So 12, you're getting 1 as a remainder, right? 24. So 25 minus 1 is minus 24 is 1. And divide by 2 again, you're getting 6 and no remainder. And divide by 2 again, you're getting 3. No remainder, right? And divide by 2 again, you're getting 1. So 3 divided by 2 is 1, right? The remainder is 1. And you have to do it again. The result is 0, remainder is 1. I have to look backwards. Look backwards to get a binary number, binary result. Now let's verify if that's correct. This is what? 2 to the 4th, right? 16. This is what? 4.
8.
Oh, 8. Yeah, 2 to the 3rd, which is 8. This is what? 2 to the zeros, which is 1, right? It's 25. Okay, so why does this works? Why does this works? It just works, right? So now let's write it down. 11001. That's a binary number we already know. But before we convert it to this point, we didn't know that. If we know it, why do we have to do it? So we didn't know it, right? However, 25 is this. No argument, accept it. 25 is this. So if I draw 1, naturally it's 1. It's like $1 is $1. Don't talk about 2's complement shit, okay? $1 is $1. Like you put in 2's complement, like 100 is, it's especially $8, but you have to say it's negative $8. I'm gonna cry. We're just talking about unsigned for now, okay? 1 is 100. No problem on that. So when we divide by 2, what's happening actually? So I'm doing the same thing over here on the other side. It's just the same, exactly the same steps. So what's really happening? So now let's look at another number. 2024. It's a 10-based decimal number. So if I don't draw a decimal point, you know the decimal point is over here originally, right? If I divide this guy by 10, what's going to happen? I divide by 10. It's a 10-based. I divide by 10. So it's moving this point to the left. I divide by 10 again. It's moving this to the left. Just again and again. So it's moving the point to the left each time. So in 2-based, if I write this down for you, I know there's a point, and I gave it a name as a binary point. So the binary point is over here, even though you didn't write it, you didn't draw it, but you know it's there. If I divide this guy by 2, what's going to happen? I'm moving this to here, right? So that's why the result is, what's the result after it's going to be 1100 will be these 4 numbers, and the remainder is what? 1. I do it one more time. What's happening? Do it one more time. It's 110, right? Remainder is? Point is here right now, right? I divide by one more time by 2. Okay? So it's the same result, right? Okay? So you know what's happening when we do this. When we use the decimal number, it's actually shifting the binary bits out from the number. That's what's really happening. So now hex. Two more minutes, okay? So 0x ff. So we are grouping 4s. For hex, we grouping 4 binary bits. One more comment. 8 bits is called what? 8 bits is what? A byte. 4 bits. Nibble. FF will be what? 1111, 111. We grouping 4 digits. Why we want to use hex? Why is that? Because it's super handy when you are assigning, especially when you are dealing with digital systems. You just directly throw 4s of digits to the pins. You just directly assign like FF. You are giving 8 pins all once. You are turning 8 LEDs on at the same time. It's just one example. So you can manipulate the digital output at the pins easily just using hex numbers. Directly, just 2 digits over here, but actually it's 8 bits. Okay? Oh, so many things to cover. I only have 50 minutes for the lecture, so see you guys tomorrow. Most of you guys tomorrow. Okay.